Today we are going to do section 3.2, the trigonometric integrals. Being that it is trigonometric, we need to review a couple of trigonometric identities and equations and such. So let's look at these real quick. The first, of course, is sine squared plus cosine squared equals to 1. And the different arrangements of it, such as secant squared plus equals to tangent squared plus 1. The way you come about it is to take sine squared, cosine squared plus 1, divide the whole thing by something, cosine. Yeah, if you divide it by cosine squared, you will get the secant squared equation. And then there are a couple other ways of arranging it. And the next batch we should remember is called the half angle formula, where sine squared equals to 1/2 minus 1/2 times cosine 2x. The purpose of that is to reduce sine squared, which is a power squared, into just something that doesn't have power, cosine, except the angle becomes doubled. And then the last one is this bunch of things that you probably don't remember seeing that, but that doesn't matter. Okay, we're just going to use it in this section. It is when you have sine some angle multiplied by sine of a angle of a different multiplier, the a and b, then the formula follows as such. And so we are going to be using those equations in this section. I want to first remind you of it. So having done that, then let's get moving. Section 3.2. First, let's look at example 3.8 on the first page. On page 273, where we are integrating cosine of something to power 3x sine of x. Now, if you look at this, you realize that we've done this before. In fact, we did it in Calculus 1. What happens is the derivative of cosine x is sine x, which means this makes for a nice u substitution situation where you let u equal to cosine x. And at that point, as you can see in your book, then everything comes out very quickly in about 3 lines, and you got to the answer. Now, however, that is nice, but what happens if the second term isn't nicely a beautiful sine x, but some other power like sine squared or some other power? Okay, so so the next example is to integrate something like that when k is an odd number, like 3 or 5 or something, not just 1. So having done that, then let's look at it. Come to find out, look at the next example, which is on the following page 274, where we're doing cosine squared x and sine cubed x. Now, at this point, the thing that looks a lot harder, but as it turns out, if you use a simple substitution, that is, you put part of the sine squared x, replace it as cosine x. So then what you end up with is that you have, instead of sine cubed, now you have cosine squared, which is the original cosine squared, and then you have the sine squared. From sine cubed, you take out one sine squared and change it to 1 minus cosine squared by the Pythagoras theorem, and then leave one sine x left. The sine x is left to take care of the u substitution, because that way you can change using the u substitution again. Let u equal to cosine x, then you plug the whole thing into a polynomial to integrate, which is much easier. Not as easier as the previous example, but still, pretty doable. And then you come up with your answer in a couple extra lines. It's still not so bad. All right. So next, let's look at next we look at the half angle formula that I showed you a little bit earlier, and we're about to have to use that. And as you can imagine, that this thing is gonna get harder, okay, as time goes on, but maybe not yet. Now, examples 3.10, we have the integral of sine squared x. Now, how would you do that? Well, if it's just sine squared, we'll stick in the half angle formula. See? And so sine squared is you plug in the half angle formula, which reduce everything to a number, and then just the cosine, no squared. Okay, it's a cosine with a number in it, but that's okay. That's just a constant, and we can take care of that. So you integrate that, and that comes out right away, as you notice. So sine squared, which is normally a kind of a tough nut to crack once you use the half angle formula, and the whole thing just falls out in one formula. So it's very nice that way. All right. So from this point on, let's flip to the next page. Where am I? 276. Now, no, sorry, 275. And now things are gonna get a bit stiff. So we have to handle it, we have a strategy. Okay, which is just a recipe. The recipe says we have all kinds of rules. Okay, please read this stuff on 276, which says that if k is odd, we're gonna follow some rules. Okay, and then a specific set of rules which involves what we just did. We'll take one sine x out for the substitution and for the chain rule application, and the rest of it we are going to change it to cosine, because we're multiplying cosine with sine. So if we change everything to cosine, then we can use the use substitution similar to what we did before and turn everything into a polynomial instead of a trigonometric equation, which polynomials are much easier to integrate. So that's the trick. All right, so knowing all this stuff, and then the set rule strategy 2 is similar. Okay, if j is odd, then you're gonna do it reverse. That is, you're gonna do it treat the cosine like it is sine in the previous example and pull the same stunt. And if they're both even, then you are going to use the half angle formula and then and do something. Anyway, so we're gonna apply those tricks in the next example. Okay, now example 3.111. Now that example looks tough, right? Instead of just sine x or something, we now have cosine to the 8th power x, sine to the 5th power x, and until we come to this strategy, in the past we have no clue how to do that, or almost no clue. I don't know if in integration by parts, I doubt it. You'll probably be spinning around 10 levels, haven't gotten anywhere or something. But this one is in comparison is not so bad. So what do? We're going to follow strategy 1, which says that excuse me, which says that for sine of being the first, we look at the coefficients, see which one's odd, because the one odd, we can kick one out, take one out, and then use it for the use substitution requirement, because du has to be sine x, and then let u equals a cosine, and then the rest of sine x we will simply turn it into use the trigonometric identity to turn it into a bunch of cosines, which sounds like a lot of work, and it kind of is, but it does work. Okay, so now the homework is getting the work is getting longer. So as you can see, we are going to the work is longer, but not necessarily more difficult. You're just following a set power rules. So we have x sine. You notice the sine power is to 5, which is odd. So we'll reduce it to 4 with an extra 1 sitting there, sine x, and then we'll take the 4 and turn it into sine squared, and then take care of it. In terms of 4, it'll be sine squared and then squared again. So sine squared, next step, sine squared got turned into cosine squared with the 1 minus in front of it. And then you will square that, which is going, and at this point, we will replace it by the use substitution, which means that, which means, as you can see, we're going to have a polynomial with a fairly high power, which is quite a bit of work, but not terrible. Okay, you can still do it, because polynomials in the end apply the power rule to each one, which isn't too difficult. It's still kind of work. It's still work, but not horribly work. So then, so you do all that stuff and keep track of all the minus and plus, and let's not mess up. And remember the power rule, and then you come up with the answer. So that is, yeah, so that's about that. So please do example 3.11 as part of your homework. Next, let's look at example 3.12 on the following page, where we're supposed to integrate the sine to the fourth power. Now, sine to the fourth power is all even, so the strategy 1 and strategy 2 is not going to apply. But there is still strategy 3, which says that if that's the case, we'll use this half-angle formula and get rid of the power. You know, the sine is the fourth power. We'll knock it clear down until it becomes no power at all. And then once it becomes no power, then we can do the integration smoothly. So to do that, then let's see. All right, there's no way around this, so let's just do it. So what you can see is you follow the formula. The sine squared, use sine fourth, okay, you reduce it to a sine squared, and each sine squared then becomes the cosine. Sticking the half angle formula stuff in there. So sine squared equal the cosine of all that stuff. You put it in there, and now you're stuck with doing algebra. Okay, now you have to multiply the whole thing out. And as you notice, after you multiply it out, you end up with a cosine squared, right? Because the whole thing is squared twice. And so what do? Well, you take that cosine squared and use the half angle formula again. So then you end up with more stuff. And then the whole thing becomes one long and somewhat painful algebra equation. But once you get all that cleaned out to become something, and then you're okay. So then you only end up with just cosine, which with 2x and 4x and stuff like that, but at least just cosine. And when that happens, then you are looking much better. And then you do the integration carefully, because now you got a lot of numbers and 4s and 8s. But if you do it carefully, then you should be able to get the right answer. Now remember, when you apply the cosine 2x on the half angle formula, this thing right here, see, cosine 2x, and you have to, the cosine squared 2x, to use the half angle formula, 2x is now your new x. So when you apply it, the result is going to be cosine 4x, because each time you apply the half angle formula, your angle doubles. So remember that. So, but once you pay attention to that detail, then everything should come out nicely. So please do example 3.12 as your homework. Next, look at the bottom of the page where there are all these formulas that I showed you earlier, which means how are we going to integrate if we have a bunch of stuff to integrate that has sine of some x and then sine of some other x. For example, what if you have to integrate, say, sine x, sine 2x, or sine 3x, sine 4x? In that case, what we're going to do is reduce this whole thing by some convenient trigonometric formula that I showed you earlier into just cosine of some number and then sine added or subtracted to sine or cosine of some other number. In other words, you don't have multiplication happening. And as you remember, integration works much better if you're only doing addition or subtraction. So we're going to knock this multiplication situation into the addition or subtraction. And with that, we will be able to come up with the answer much easier. So let's look at an example of that, such as, for example, the next examples, example 3.13, where you're supposed to integrate sine of 5 of x and cosine of 3 of x. So sine of 5, so you stick that formula that I just showed you in there directly. Okay, sine 5x, cosine 3x, you apply the formula, the sine of, I don't know, a plus b, a minus b, something. And but in the end, you end up with just sine, a simple sine, and minus a simple cosine. That is, no multiplication involved, which means you can integrate each one individually quickly and come up with some answer. So, and the only hard part about applying those formulas is make sure you don't mix up A or B. That's all. Other than that, it's very straightforward. Now that's example 3.13. Please do that as your homework. Now next, we're on page 277. Let's look at some of the integrals of the secant. We're now paying attention to secant and tangent. Now the integral of secant squared, of course, is tangent. That's just from the fact that the derivative of tangent is secant squared. The second rule, the integral of secant tangent is secant. Again, that's because the derivative of secant is secant tangent. Number 3, the integral of tangent is the natural log of secant. That's still pretty decent because the tangent is sine over cosine, and the derivative of cosine is sine, right? So you can use the use substitution very quickly. You can even see it in your head that you just use this use substitution, and that should fall right out, and that'll become natural log of something, 1 over cosine, which is secant. And then finally, we have the integral of secant x equal to whatever that says. Now that one, your book says you have already learned this. Now, have you learned this? Do you know that what integral of secant x is? Well, you might find that hard to remember. You know, where did you learn it? And furthermore, if you don't remember how to do it, how would you do this? Okay, I mean, how do you do the integral of secant x? Do you use use substitution or something? No, and because there's no obvious way to do this thing. But actually, we have done it in Calculus 1. And I want to remind you how it was done, because it's somewhat interesting. And what you do is, to calculate the integral of secant x, what you do is this. Okay, you calculate secant x like such, sec x dx. Now, off the top of my head, I can't think of what to do. Integration by parts? Nah, I don't think so. Use substitution? What are you gonna? I mean, you can't figure out what the where's the chain rule applying. This is not tangent. See, if it was tangent, that would have worked better, but it's secant, so that's not going to work. And in Calculus 1, we did this in Calculus 1, and did it by using a trick, a neat trick that is how that does. So in Calculus 1, I want to remind you how to do this, just because it's neat. Okay, and so what you do is you multiply this thing, secant x plus tangent x dx. You multiply by this thing and then divide by the same thing, secant x plus tangent x. And why are we doing this? Because yeah, that's just what we do. Okay, and then so being that you're multiplying by the same and dividing by the same thing, this is just 1, so it's okay to do this. But the question is, why am I doing this? The next trick is then you let u equals to this stuff on the bottom. That is, you let u equal to secant x plus tangent x. And then what is du? Then when you calculate du, derivative secant is secant tangent. Okay, if you don't remember that, refer to your list of derivatives, and then the derivative of tangent is secant squared. Okay, secant tangent. Where's my tangent? Tangent. Secant tangent. Okay, secant tangent. The derivative of secant is secant tangent, and derivative of tangent is secant squared. All right, and then which is fine, but look at this thing. What is this du? Du is exactly the stuff, every single thing on top, all of it. Okay, here's secant squared, and here's secant tangent. So this, whereas u is everything on the bottom. So this entire integral gets transformed into this neat trick, du over u. And therefore, it equals the natural log of u, which is, and u is secant x absolute value, because natural log can't take negative numbers. So natural log of u, and which equals to the natural log of, stick u back in there, which is secant x tangent x. And plus your constant, of course. So that's how the secant is being integrated in Calculus 1. So if you don't remember how that's done, don't feel bad. It's no big deal, okay? Because it's not obvious at all. As you can see, it requires a very neat trick and how this is done. But nevertheless, we're going to need to remember this piece of information, that the integral of secant is natural log of secant and secant plus tangent x. And now that we have talked about this, I also want to mention the integral of the cosecant. The cosecant will be proven in almost identical way, which I have it written down here, and looks practically the same. Okay, so I will just show it to you. To integrate the cosecant, you multiply cosecant plus cotangent, and after that, everything will come out almost identical to how the secant works, and you end up the answer being negative natural log of cosecant plus cotangent. So it's very similar, except with cosecant and cotangent, you have to stick a negative sign in front. Otherwise, it's almost identical, and that will be how you do the integral cosecant. But we're not paying too much attention to the cosecant or cotangent in this section. We're just focusing on the secant and the tangent. So now that we have all the secant and tangent integrals looked at, let's look at example 3.14. And remember, the derivative of the secant is secant tangent. Being that we're considering the derivatives and the integrals all the time at the same time, sometimes you can get confused. If you get confused, refer back to your chart and figure out which way is the derivative, which way is the integral. And so let's look at example 3.14, where it says that we're supposed to integrate secant to the 5 power x and then tangent x. Now, there's remember, the derivative of secant is secant tangent. So if we take one secant out of here, then we'll have du taken care of, because we'll have secant to the power 4 and then secant tangent, which is the derivative of secant. So that's what we're gonna do, is as your book says, that we'll rewrite secant 5x tangent x as secant 4x and then secant x tangent x, because the second part is for the du. And then we'll let u equal to secant 4x, and then everything will come out nicely. All right, so please do this example as well, 3.14. Next, let's look at the problem-solving strategies on page 278 following. Now, the strategies might sound confusing. It's far better to use the strategies by simply working an example and then follow the strategies carefully. So let's look at example 3.15, where it says we're taking the integral of tangents to the power 6 and secant to the power 4. Okay, so what does that mean? So the tangent, so then the j is even, so we can do strategy 1. If j is even, and so on. So following strategy 1, we are going to write down secant 4x as a power 2 less. So we'll write down secant squared x, and then with the secant squared x, and that we took out. The reason we took out secant squared x is because the derivative of tangent is secant squared, and we're going to take advantage of that fact. So then we have the original tangent is still there, so we'll write that down, tangent 6x, and here's our integral. So we haven't made very much headway yet, but next we're going to replace this with tangent, which is according to the trig identity. The secant squared is tangent plus 1, says right here. Okay, so then this is tangent 6x, and then secant squared equals a tangent squared plus 1. So tangent squared x plus 1, and then times secant squared x, and then dx. Okay, so we have all that stuff. Then we are going to, at this point, we will remember the derivative of tangent is secant squared. So we got the du taken care of. Okay, we need this part. And then at this point, we're just going to use the u substitution for tangent x. So u is going to be equal to tangent x. And then du is going to be, of course, secant squared x dx. And at this point, then we have gone past the hurdle. Okay, we jumped over the hurdle, and now we're good to go. We're on our way home. So then it becomes u to the power 6 times, what is that? U squared, okay, plus 1, and then du, right? Yeah, I think so. So at this point, then what we have left is just a matter of grunt work, which then it is finished here, and if you don't mess up the grunt work, everything should come out just fine. So please finish the example 3.15 as your homework. Next, let's look at example 3.16, where we're integrating tangent 5 to the power 5x and secant to power 3x. Now that is in the case where k is odd. K is the power of the tangent. So then if k is odd and stuff, we'll go back previous page and look at strategy 2, which we're going to follow. What are we going to do then? Then we're going to write this thing as secant tangent. Why is that? Because the derivative of the secant is secant tangent. So that's why we're going to do this. So following rule 2, we will have k is odd. Okay. So this whole thing will be written as secant tangent. Tangent will write everything down by 1 power because we need a secant tangent at the end. So everything will reduce by 1 power. So that's tangent 4x, secant 2x, and then times tangent x secant x dx, and that's the new integral. We're just rewriting it so that there's a secant tangent at the end, because the derivative of the secant is secant tangent. And then the next step we're going to do is we're going to get rid of tangent by plugging secant in there with the formula that tangent squared equal to secant squared minus 1. That's one of the trig identities we mentioned earlier. So this thing will use secant squared equals to tangent squared, etc. So to do that, that will be, so tangent squared equals to secant squared minus 1. Okay, we have tangent to the power 4th, so that's squared. Inside here is tangent squared. Okay, so together makes it the 4th power. And then we have secant squared x. We'll keep the secants in here. So everything is getting turned into secant except for this part, because that part is to take care of the du. So, and then the rest we have tangent x secant x dx. So at this point, we're going to let u equals to secant squared. U equal to secant x. So that du becomes tangent secant equals to tangent, du equals to tangent x secant x dx. And so with that, we can rewrite our integral into u is secant x. So that becomes a u squared minus 1, then squared again, and then another u squared, okay, for that. And then the whole thing, the rest of it is just du. And then you multiply this thing out, and it's a polynomial. So it integrates fairly easily. Let's double check to make sure that I got everything right. So what do I have? It says U6. Did I get something wrong? Let me check. Tangent 5, tangent 6. What? Oh, I was looking at the wrong problem. This is correct. So the rest, please finish the rest of the grunt work and do example 3.16 as your homework. Next, example 3.17, when we integrate tangent to the 3rd power, which sounds hard until you realize that all you have to do is stick in a quick substitution, replacing tangent squared, that is the squared part, with secant squared minus 1, and then everything will come right out. Please do that as your homework. Next, let's look at example 3.18 on page 280. Now, the 3.18 is exactly the problem 63, I think, of the previous section. So if you already done that, you can, just sleep through this example, I guess. But if you had trouble, then let's talk about it. The way to do it is first you let u equal to secant x, and then but you let dv equals to secant squared x. So because why is dv secant squared x? Because the derivative of tangent is secant squared. So you're arranging it in anticipation of the tangent coming, which is not something you normally do, but this is a trick you pull in this particular case. So once you've done that, then so u is secant x, dv is secant squared x, then du then is derivative of secant is secant tangent, and then v you integrate secant squared, which becomes tangent x, right? That's why we did it. So you put all that together, and what do you get? You get you look pretty good, but not that much better, because now you're stuck with tangent squared secant x. So now what? In fact, that looks even harder, right, than the original secant cubed. I mean, which is better, secant cubed to integrate or tangent squared secant? It doesn't seem to be a big improvement. But this is where you pull a stunt, is a quick stunt of replacing tangent squared with secant squared minus 1, which is the identity that we mentioned earlier. Tangent squared equals the secant squared minus 1. Once you plug that in, then what do you have? Then you clean that up, and you end up with something that has secant cubed again. But it's which might seem like a waste of time until you realize that's a negative, it's minus. So that's good. Why? Because being that it's minus, you can slap it on the other side and add it up so that you have two of them on the other side. Now, in the meantime, you still have to integrate secant x dx. As you remember, a little earlier, we did integrate secant x with a trick, right? And your book didn't bother to explain that, but it's true. If you secant x is integrated, and there's the formula for it, and the integral of secant x, as mentioned a few pages earlier, is natural log of secant x plus tangent x. So with that, then you got the answer. The answer is then look a little further down, then you have two of them, okay? Because the minus secant cubed, as you see on top there, on the top right corner, is simply slapped on to the other side, where you also have a secant cube, so you have two of them. So then the whole answer is just that thing divided by half. That comes up with a decent answer, which is not that short, but still it's not horrible, okay, for calculating the integral of secant cubed. Now you should write down the integral of secant cubed, because we're going to need it later when we do something that's even harder, and the integral of secant cubed is actually the answer to that question. So yeah, so make a note on the integral of secant cubed so that we can refer to it later, because it's going to come up. So please, if you didn't manage to do problem 63 from the previous section, then please do example 3.18 as your homework. Now, in the previous example 3.18, when we are integrating secant cubed, we did pull off a trick that reduced the power, okay? So we right around here, where we start out with secant cubed, and then look at the second line, we end up with something like integral of tangent squared secant x. So the power got knocked down, but we also gained tangent squared. Now that trick can be generalized into the formula on the next page, the reduction formula, which says that when you integrate secant to some power n, in general, you can follow this particular formula to knock it down or something. Where's the tangent? Well, I guess they went all the way down to the bottom, maybe? Yeah. Anyway, right. Now, let me see this. I see that the tangent squared is replaced by secant squared and then cleaned up a little bit. But anyway, what we did in example 3.18 can be summarized in general to be these two formulas. They are called reduction formulas because they are somewhat helpful, that you just keep applying them and eventually you can come up with the answer without going through all the detailed work. So to see an example of that, see how that works, let's look at the integral of secant cubed again. But this time we're going to use the reduction formula. So how does that work? Then, so how will we integrate secant cubed by the reduction formula? We're going to follow it exactly as is. Okay, following the reduction formula, we have this equal to 1 over n is equal to 3 in our case. I'll write that here. N equals to 3 in the formula. So that equals to 1 over n minus 1, which is 2. Then secant n minus 2, which is 1. So just secant x, tangent x. And then plus n is 3. 3 minus 2 is 1. 3 minus 1 is 2. So 1/2 again. Integral of secant n minus 2, which is just secant x dx. So that the reduction formula got us to the secant x. And then what we're going to do is, remember the secant x is already given the answer. We calculate it to be just secant x becomes, what is it? The natural log of secant tangent, right? I mean secant plus tangent, s secant x plus tangent x, like that. And then that's about it. And don't forget to multiply by half. And once we've done that, then see the whole answer. Then instead of the integration by parts, which about worry out, now we just follow the formula and the whole thing, and also remember what the integral of secant is. Then the whole formula comes out in one strike. Okay, so it's pretty nice that way. The reduction formula can be useful sometimes, and the tangent version works the same way. Yeah, actually we're about to do the tangent version. So please do example 3.19 and example 3.20, both of which are very short because the reduction formula reduces work. That's why it's called that. So we have come to the end of the section. There are a lot of homework. That's the examples in this section. Please do them patiently. I know they are quite exhausting, right? It's grunt work. But we are in Calculus 2 and beyond, there are often quite a bit of grunt work. You gotta, you know, there's quite a bit of heavy lifting actually. So you need to hit it hard, and but not necessarily taking more time. Just use the allotted time. It might take you longer to get through a section, but there's nothing wrong with that. So please do your homework problems on page 283, problems 79, 83, 85, 86, 89, 93, 95, 97, 101, 103, 9, 11, and 13. And afterwards, I will talk about all the problems in the next section. I mean, in the next video.